Okay, next guy. Got a product here. So use the product rule for differentiation. So plane first, derivative of the second, plus plane second, derivative of the first. Product rule. And again, you do not have to show this step. But it helps people learn the product rule. So plane first, I'm going to leave that alone. Derivative of the second. There's my new format. Repeats. Natural log of the base, derivative of the exponent. Repeats. ln of base, derivative exponent. Then I'm up to the plus sign, so I'm going to leave it alone. Then I get to the logarithm, 1 over the argument, derivative of the argument. And so cleaning this up a little bit, and honestly, I just wouldn't do much here. I would probably say that this was 4 pi to the 4x, natural log of 3x plus 1, natural log of pi, and then plus 3 pi to the 4x over 3x plus 1. There really just isn't much you can do to simplify it. If you wanted to, you could factor out that pi to the 4x, but there's really no point. That's about as much as you can do. But the point there kind of was quotient rule. So kind of recapping that when I have a form of number to a variable, so that's up at the top of the page, number to a variable, it's repeats, natural log of base, derivative of the exponent. And that's what I had here. Number to a variable, repeats, natural log of base, derivative exponent. Number to a variable. Let's look at the next guy. And my form here is variable to a number. Like, say, x cubed. And the derivative of x cubed is 3x squared. And so my point here, be very careful, and you have to look at your forms and pick the correct method for the form here. So this one, the answer is multiply by the exponent, decrease the exponent by 1. That's the rule that we have to use here. And so you have to start being very careful about what your exponentials look like. Is it a variable to a number? Well, then it's repeats. Or not repeats. If it's a variable to a number, multiply by the exponent, decrease the exponent by 1. But if it's a number to a variable, it's repeats, natural log of base, derivative of the exponent. That you've got to look very carefully at these forms. And so really the same thing here. It's a variable to a number, and moreover than that, I've got an inside function of the natural log of x and an outside function of an exponent of pi. Because remember, pi is just a number. So I'm going to start on the outside. It's going to be a chain rule. Start on the outside, multiply by that exponent, decrease the exponent by 1, but then chain rule times derivative of the inside. So there's derivative outside derivative inside. And remember, when I'm doing the chain rule, I don't change that middle, that first pass. And then doing the derivative of the inside, very explicitly, 1 over the argument, derivative of the argument. 1 over argument, derivative argument. And so I would say this problem has an answer of pi times the natural log of x of pi minus 1 all over x. And this does not simplify. This exponent right here, I know someone says, oh, the power rule for logarithms, that exponent can come down in front. No, it can't, because this is an exponent on the entire logarithmic expression. It's not an exponent just on the x. The power rule for logarithms talks about that exponent coming down in front when that exponent is on just the argument, not on the entire logarithmic expression, just the argument. So this really doesn't simplify any further. Okay, there is one last exponential form. So far the derivatives of the form a to the x and e to the x, a constant raised to a variable, have been discussed. And the form x to an a, variable raised to a constant, has been reviewed. Each form, a constant raised to a variable and a variable raised to a constant, has its own rule when differentiating. There is one last form, a variable raised to a variable. To differentiate a function that has a form of a variable raised to a variable, we will use logarithmic differentiation. Now there is another way to do it, but in my humble little opinion, logarithmic differentiation is the easiest way to do it, so that is what we will do. So, next problem. Differentiate the following. So I look at my form here, and my form here is a variable raised to a variable expression, but a variable to a variable. And so that's going to be my key to use log differentiation, which we just learned a while ago. But step 1 was to take the logarithm of both sides. Step 2 was to simplify. So for the power rule of logarithms, that exponent can come down in front. And the 3, differentiate. 1 over the argument, derivative of the argument. But this is really implicit differentiation. So derivative of y is 1. I just differentiated y, so you can follow it by dy dx or y prime. I'll go with y prime. It really is implicit differentiation on this side, or it's implicit differentiation. So 1 over the argument, derivative of the argument, just differentiated y, followed by dy dx or y prime. Over here, a product rule. Plane first, derivative of the second, plus plane second, derivative of the first. Plane first, derivative second, plane second, derivative first. So keep going. So I have 1 over y prime equals x squared. 1 over the argument, derivative of the argument. Clearly I wouldn't need the times 1, but I'm just being very specific each time. Then I'm up to the natural log, and the derivative of x squared is 2x. So let's clean that up a little bit. So I have 1 over y prime equals x plus 2x, natural log of x. Notice this doesn't become 2x squared. Your arguments or your logarithms aren't going to change unless you used a property of logarithms. There is not a property of logarithms that says what to do when you multiply by 2x. Your arguments of your logarithms won't change unless you did a property of logarithms. So that's going to stay in x. And then I multiply both sides by y. Over here, those are going to cancel. And so I get y prime equals y times x plus 2x, natural log of x. And then replace y with what is equal to. So recall that y was x to the x squared. And so I get x to the x squared times x plus 2x, natural log of x. And there is a perfectly good and happy answer. There is good enough. But again, just to show us sometimes things that might happen, what you might see in the computer, and just to raise our algebra skills a little bit, I could note inside those parentheses that I could factor out an x. And then being very, very explicit, that's x to the first. And now I'm multiplying with the same base. And so I could add my exponents and get a wonderfully perfect answer of x raised to the x squared plus 1 times 1 times the quantity 1 plus 2 natural log x. You couldn't pay me to care about that. This is a good enough answer, but I see this every once in a while on the computer, so I just want to alert people to it. Okay. Moving on. We're getting close to the end. Other base logarithms. Now, we can memorize a whole bunch of calculus formulas for other base logarithms, but we're not. First, a definition. For any positive number a not equal to 1, y equal log base a of x is the inverse function of y equal a to the x. So we've kind of already talked about that. And then the facts that logarithms and their associated exponential functions are inverses. So log base a of a to the x is a, or x, excuse me, and a raised to the log base a of x is x, because exponential functions and their associated logarithms are inverses. Now, like I said, we can learn specific calculus formulas, but I think that's the hard way. We're going to just use an algebra formula, the change of base formula. Log base a, or change of base formula, log base a of x is equal to the natural log of x over the natural log of a. And you should memorize that, because that is the way we're going to go about doing logarithms of other bases. So find the derivative of the following. So the first thing I'm going to do is I'm going to use that log base a of x is natural log of x over natural log of a. So y equal log base 25 of e to the x minus log base 5 of 3 to the x immediately becomes natural log of e to the x over natural log of 25 minus natural log of 3 to the x over natural log of 5. Then, further, this becomes this, 1 over the natural log of 25 times x. Natural log of e to the x, that equals x. And that natural log of 25 is just a number, so bring it out as a coefficient. And the same thing here, that's 1 over natural log of 5 times the natural log of 3x. Students want to make logarithms so much harder than they have to be. But if it doesn't have a variable in it, it's just a number. So these guys are just coefficients. I'm going to have to end the video here, and we'll pick up right where we left off.